Hi, so in this video we're going to talk about applying row operations to a matrix with a known determinant and seeing how the different types of row operations we've worked with in the past um, affect the determinant. And so we're going to let A be a 4 by 4 matrix whose determinant is -2. And the exact form of the matrix is not important, and there's no way we could know what it is anyway. When we perform these operations, I really want you to think about or picture um, a 2 by 2 matrix and maybe some sort of rectangle or parallelogram in R2, and just note that the ideas expressed or the principles that would apply to a 2 by 2 matrix are no different in a 4 by 4 matrix. So, with that perspective, let's start with this first question. Let M be a matrix obtained from A by taking R1 and replacing it with -4R1. So if we imagined what would happen to a parallelogram, or maybe even just a square, what you're doing is you're taking one of the dimensions of the square and you're pulling it down, right? You're flipping it and stretching it out by -4. So any positive area that you had is going to scale by 4 and turn negative. Any negative area you have is going to scale, or a negative area that you have is going to scale by 4 and turn positive. So if we want to ask ourselves what the determinant of M is, the matrix that you get from doing this, well, the determinant of M, what's that going to be, is going to be -4 times the determinant of A. So it's going to be -4 times -2, which is 8, right? If the matrix A sort of represents a four-dimensional parallelogram, however you want to picture that, with sort of sine volume -2, by swapping one of its dimensions in the other direction and stretching by 4, we've turned that into something with signed volume 8. Alright. And that's always the case for any replacement anytime you have an operation like this. So let n be obtained from A by applying, taking R1 and replacing R1 with R1 itself, and from that we're going to subtract 3 times R2. And what's the determinant of n? So what I want you to now imagine is a parallelogram, and what we're doing now is we're shifting. R2 is going to stay the same, but R1 is going to shift over by some amount, right? It's going to shift over by some number of copies of R2. But in shifting it over, you don't actually change the area of the parallelogram, right? We're just moving things through. So whenever we have an operation like this, the determinant of the resultant matrix doesn't change from the original. So what we know about the determinant of n, is that it's actually equal to the determinant of M. In this case, that's -2. Alright, Alright. And finally, our last question here is, okay, let P be obtained from A by swapping two of the rows, row 1 and row 4. What's the determinant of P? So what I want you to now imagine instead is you have some sort of parallelogram, and now you swap two of the dimensions, right? So I take a parallelogram and I swap the two. Now the area of this parallelogram doesn't change, but the orientation doesn't change, right? The side that used to face you is now on the other side. So when you swap like that, right, positive becomes negative and negative becomes positive. The signed area or the signed volume of this figure has switched. So when we take the determinant of P, that's going to be minus the determinant of A. So that's, of course, 2. Alright, thank you very much. I'll see you in the next video.